Yes, here we go. Yes, good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exams and do absolutely well. Okay, still on the subject, beautiful subject, chemistry. Chemistry is not just a subject, it's a beautiful subject. It gives this heavenly feeling. So, still on the beautiful heavenly subject of chemistry, still on the beautiful heavenly subject of chemistry. I know I have a very special affinity towards chemistry, and that's obvious anyway. Okay, still on the topic stoichiometry. The last time we looked at stoichiometry, we were trying to look at key dot concept, but for all of those questions, we were given balanced equations. But this time around, we are going to be dealing with stoichiometry, having to construct the chemical equations by ourselves. Recall that without a balanced equation, then there is no way we can get things done as far as stoichiometry is concerned. Of course, the link to the last lectures telling us how to navigate in stoichiometry, what we need to do, is in the description to this lecture video, so that in case you mix out on that, you can quickly run through things so that we are on the same page. Aside that, let's get into the fray of things. Okay, the first question we have stated, how many grams of oxygen can be produced from 4.50 gram of potassium triacylchlorate 5? Okay, I think that means from decomposition of potassium triacylchlorate 5. KClO3 is potassium triacylchlorate 5. So we want to look at how many grams of oxygen we can produce from that. When you say potassium triacylchlorate 5, this is potassium triacylchlorate 5. So how many grams of oxygen can be produced when this is decomposed? Of course, you want to produce oxygen here. You're looking at oxygen gas. Okay, if you remove oxygen here, the fact that 3 is here and oxygen exists as O2, I need to put 2 here. That means this is 3. Then looking at the potassium chloride I'm left with, this is the potassium chloride, and this way what I have is a balanced equation for the decomposition of potassium triacylchlorate 5. Of course, when you look at things from 4.50 gram of potassium triacylchlorate 5, so what that means is that I am being given the mass of potassium triacylchlorate as 4.50 gram. So that ultimately makes this my key. And I'm now told to look for the grams of oxygen. How many grams of oxygen? So that means I am looking for the mass of my oxygen, and that invariably makes this my door. But look at it. If I don't have a balanced equation, then there is nothing I can actually do. Every other effort I put in is nil and void. Okay, so what we're going to do here now is, first of all, recall the process. I need to convert my key to mole. So mole equals to mass over molar mass, and in here this is 4.50 divided by, when you say potassium triacylchlorate 5, KClO3, if you calculate the relative molecular mass, that should be 122.5. 4.50 divided by 122.5 will give you 0.037 mole. That way, I have just converted my key into a standard key, and I now have that in mole. I then can use that to unlock this. And how do I can use that to unlock for my oxygen. Looking at this balance equation, 2 mole of KClO3, potassium trihydrochloride 5, is stoichiometrically equivalent to 3 moles of oxygen. So the implication of that is if I'm saying 2 divided by 3, 2 over 3 from a balanced equation, then in reality, the mole of KClO3, which is 0.037 divided by the mole of oxygen. So mole of oxygen here is going to be 3 times 0.037 divided by 2. So from these, I am going to get 0.055 mole. That is the mole of oxygen in this case. But I was not told to look for the mole. I was told to look for the mass. So it is like this. Convert your key to mole. When you convert your key to mole, use your mole, which is now the key, to unlock the door. In this case, whatever you are finding, you're going to get it in mole. Convert whatever you have in mole for what you're looking for into what they want. If they want it in mass, convert the mole to mass. If they want it in volume, convert the mole to volume. If they want it in terms of number of particles, convert it to number of particles. So in this case, they want it in mass. So since mole equals to mass over molar mass, then mass will be mole times molar mass, and in this case 0.055 times the molar mass of oxygen here is 32. 16 times 2, 32. So 0.055 times 32 should give us 1.76 gram. That is the mass of oxygen. Let us imagine that in this question, we were told to calculate the volume of oxygen. Let's imagine we were told to calculate the volume of oxygen in this question, volume of oxygen produced. It is very simple. Recall that I talked about mass-volume relationship in the last lecture, talking about stoichiometry 1, where I talked about key door concepts, and I made reference to so many formulas that we use under stoichiometry. I talked about mass-volume relationship. The link to that lecture video is being dropped in the description to this lecture, so you can always check that out. So talking about mass-volume relationship, we've said for solid reactants, mole equals to mass over molar mass. But when we're talking gases, mole equals to volume over gas molar volume. And I told us that gas molar volume means 22.4 dm cube. Gas molar volume means 22.4 dm cube. So what that means, that is the space occupied by 1 mole of a gas, 22.4 dm cube, or you say 22.4 liters. The implication of that is that I could say mass over molar mass equals to volume over molar volume. I could say that, whereas because this represents mole. So imagine I was told to look for the volume of oxygen here. Very easy stuff to deal with. Since the mole of my oxygen is 0.055, then it means my volume, if I try to make volume the subject here, my volume is going to be mole times gas molar volume. So the mole here is 0.055 times 22.4 dm cube. So volume of oxygen here is going to mean that is 1.23 dm cube. That would be the volume of oxygen. Like, stoichiometry is so easy. Just navigate the right way, use the right formula, follow the right process, and you'll be good to go. So that ends question 1. Okay, moving on to question 2. Lithium hydroxide reacts with gaseous carbon dioxide. Now, saying lithium hydroxide reacts with gaseous carbon dioxide is just enough. Now telling you to form solid lithium carbonate and liquid water is just like giving you a very good hint into what you are expected to do. Under normal circumstance, this should not be in the question because It's now more like you're being told the product. No, you should not be. So let's try to strike a very good equation for that. Lithium hydroxide reacting with gaseous. This is lithium hydroxide reacting with gaseous carbon dioxide. Okay, to form, as you were told, the lithium carbonate. Lithium. Now you can see that Charles carbonate 4 is CO3 2 minus. When you look at lithium, lithium is your third element, hydrogen, helium, lithium. So that this is what lithium looks like, 2 1 2 1. Lithium looks like 2 1. For lithium to attain duplet electronic configuration, it needs to give out this one electron, so that lithium now becomes Li plus. But of course, this radical triazocarbonate 4 is a 2 minus, so we will need another Li plus so that this can now balance this. That is why your lithium carbonate is going to be Li2CO3 to form solid lithium carbonate and liquid water H2O. Liquid, then solid lithium carbonate. Now let's try to balance that. Let's try to balance that. Okay, lithium, I have 2 here, so I need to put 2 here, and taking one oxygen, putting here. Okay, this looks balanced. 2, this is 2H2O. This is the balanced equation here, and we can now move into solving. So getting back to the question, we now have a balanced equation. Lithium hydroxide reacts with gaseous carbon dioxide to form this. How many grams of carbon dioxide can be absorbed by each 1 gram of lithium hydroxide? What they are saying there is that the mass of lithium hydroxide is 1.00 gram. So how many grams of carbon dioxide? So we're looking for the mass of carbon dioxide. So we have to deal with our key first. Now, talking about our key, mole, we have to convert it to mole, which is mass over molar mass. This will be 1.00 divided by lithium is 7, as you can see. 7 plus 1, 8, 8 plus 16, 24. 1 divided by 24 should give us 0.042 mole. That way, I have been able to convert my lithium hydroxide, that's the key, to mole. And then the next thing is I can then use this to unlock this. How do I do that? I'll be saying, okay, 2 mole of lithium hydroxide is stoichiometrically equivalent to 1 mole of carbon dioxide, so that if I'm saying 2 over 1, it means I'm saying 2 over 1, then mole of this divided by the mole of this. So that is 0.042 mole divided by mole of carbon dioxide. So mole of carbon dioxide is going to be 1 times 0.042 mole divided by 2, and that's going to give you 0.021 mole. So having said that, now we can convert that mole to molar mass, to mass. So mass of CO2 is going to be mole of CO2 times molar mass, in this case 0.021 times the molar mass here is, for carbon dioxide, is 44. If you calculate 44, in case you don't know how to calculate relative molecular mass or molar mass, or what we call formula mass, the link to that lecture video on how to calculate that is in the description to this video as well. So I'm going to give you 0.92 gram, and that is how that works. So that is the answer to question 2. So moving on to question 3, which talks about combustion. Now it says, what mass of oxygen is consumed in the combustion of 1 gram of propane? When you talk about combustion, it simply means something reacting with oxygen. So in this case, they said propane. So propane is C3H8. That belongs to the alkane family. Okay, C3H8, combustion. Okay, oxygen. When you talk about combustion of alkane, Usually carbon dioxide and water is formed when there is complete combustion. So C3H8, that is my propane. With oxygen, okay, let me put it there, propane. So having this, I begin to think 3CO2, okay. Having 8 hydrogen, I begin to think 4H2. 4H2 gives me the hydrogen, but you know, it is about carbon dioxide and water. That is what will be formed when you have combustion. So, 3 times 2, 6. 6 plus 4 oxygen here, that makes it 10. So if I put 5 here, that just makes a balanced equation, because I have 3 times 2 oxygen here, then 4 oxygen here, that makes it 10. 5 times 2, 10. So the question says what mass of oxygen is consumed in the combustion of 1 gram of propane. So it means that my propane, the mass is 1.00 gram. So converting this to mole will be mass over molar mass. In this case, 1 over 44 as well. 1 over 44, because 12 times 3, 36, 36, 1 times 8, 8, 36 plus 8, 44. 1 divided by 44, so that the mole of propane is going to be 0.023 mole. That is what is the mole of propane. We're told to look for the mass of oxygen consumed. Mass of oxygen consumed is the question. So in this case, I'd say 1 mole of propane, C3H8, is stoichiometrically equivalent to 5 mole of oxygen. So in this case, that means 1 over 5 equals to 0.023. If it's 1 over 5, then mole of propane divided by the mole of oxygen. Mole of oxygen. So mole of oxygen comes in, mole of oxygen equals to 5 times 0.023. That is 0.115 mole. That is the mole of oxygen. But of course, I'm told to look for the mass. So the mass is going to be mole times molar mass. So 0.115 times, for oxygen, that's 16 times 2, 32. 0.115 mole times 32. That will give me 3.68 gram. That is the mass of oxygen required for complete combustion of propane, and that ends question 3. Okay, yes, moving on to question 4, we have another question, but this time I think the tempo is going to be a bit up. It says 4 gram of an impure sample of iron was dissolved. 4 gram, emphasis on the fact that this is not pure. 4 gram of an impure sample of iron, okay, we have 4 gram of an impure sample of iron was dissolved in an excess 0.40 mole per dm cube HCl. Okay, 4.0 gram of an impure sample of iron was dissolved in an excess 0.40 mole dm cube HCl solution. Okay, what I want to do first here is my equation, so that I say iron, which is a solid, was dissolved in HCl solution. Okay, this is aqueous. Whenever iron reacts with HCl, you need to know that it is the lower chloride that will be formed. But when iron reacts with chlorine gas, it is the higher chloride, iron 3 chloride, that will be formed. So in this case, iron reacting with HCl is going to give me iron 2 chloride, FeCl2. I'm going to put 2 here, and then this is going to give me hydrogen gas. Of course, this is it. So now that I've done this, I was told 4 gram of an impure sample of iron. Now, because that this iron is impure, never forget that. When something is impure, it means that you cannot use that to calculate in stoichiometry. You cannot use that because it is impure, and certain things will not take part in the chemical reaction. The impurities will not take part in the chemical reaction. So once something does not take part in a chemical reaction, then you cannot use it for stoichiometry. So the mass of this was 4.0 gram, but we were told it was impure. So the fact that it was impure means the whole of the 4 gram will not take part in the reaction. Therefore, we cannot use this as our key. It is not possible. Was dissolved in an excess 0.40 mole dm cube. So the concentration of this is 0.40 mole per dm cube. Okay. Solution. That is that if 1.12 dm cube of hydrogen gas was liberated, okay, we were given volume of hydrogen gas liberated to be 1.12 dm cube. Calculate the mass of iron used up. Now here we are. The first thing is this. It is still stoichiometry. I cannot choose this as my key. No, I cannot choose this. When I come here talking about concentration, we all know that concentration equals to number of moles divided by volume in dm cube. Fine, I am given this. I am given concentration, but I was not given the volume. Therefore, I cannot convert this to mole. If I am to convert this to mole, that means number of mole here is what? That means my mole here is concentration times volume, and I have the concentration, but I don't have the volume. So that means I cannot use this as my key, as I cannot get this in mole. So this out, no information about this. I was given information about hydrogen gas, and that is the volume that was liberated from the equation. This is what I can use as my key. Recall that mole equals to volume over molar volume. Therefore, this will mean 1.12 dm cube divided by 22.4 dm cube. So my mole here is going to be 0.05 mole. Now with this, I can unlock anything and I can proceed with my calculation. I was asked here, the first question, what mass of iron was used up? So I'll use this to know the mass of iron that actually took part to give me this. The whole of this 4 gram, as it were, I cannot use it because not all of the 4 gram will take part in the reaction. The impurity will not take part. So let me use this to decode the mass of iron that actually took part in the reaction. So talking about question A, mass of iron used up. So I'll simply say 1 mole of hydrogen gas is stoichiometrically equivalent to 1 mole of iron. The implication of that is 1 over 1 equals to 0.05 mole divided by mole of iron. Mole of iron will then be 0.05 mole as well, because 1 comes in, 1 comes in. It makes no difference. So now that I have this, then the mass of iron is going to be mole times molar mass. So the mole here is 0.05 times iron is what? 56 times 56. That is 2.8 gram. So 2.8 gram is the mass of iron used up, is the mass of iron that actually took part in the chemical reaction to give us 0.05 mole of hydrogen gas. Now, B says I should calculate the percentage purity. B says percentage purity, that's percentage of the pure substance. So percentage purity is the pure substance divided by the impure substance times 100. In this case, the pure substance is the actual substance that took part in the chemical reaction. So, and in this case, that is 2.8. 2.8 divided by the impure substance is 4 times 100. So that is 70. That's going to give us 70%. So that is the percentage purity. The pure substance is what actually took part in the reaction. And moving on to C, we were told to calculate the actual volume of HCl. Okay, moving on to C, we were told to calculate the volume of HCl. Recall what I said here. for me to be able to, but this is, I was only given concentration here. So if I'm looking for volume, it simply means I should make volume the subject. If volume comes here, concentration will comes here, if volume comes here, concentration comes here. So volume here is actually number of mole divided by the concentration. In this case, I have my concentration, I don't know my mole. So the implication of this is that I still need to use this 0.05, which is my key, to get the mole of the HCl, because without getting the mole of the HCl, then I cannot calculate actual volume of HCl used up. So what this means is that I would say 1 mole of hydrogen gas is equivalent, stoichiometrically equivalent to 2 mole HCl. So if I say 1 over 2, 1 over 2 means 0.05, because that means mole of hydrogen gas from the equation, then mole in reality 0.05 mole divided by mole of HCl. So 1 will come here, that's mole of HCl equals to 2 times 0.05 mole, and that should give you 0.10 mole. That is the mole of HCl. Therefore, I can then bring this into play now. So the volume used up equals to mole, and the mole now is 0.10 mole divided by the concentration, which is 0.40 mole per dm cube. That is 0.25 dm cube. This is in dm cube. For me to convert dm cube to cm cube, I could leave my answer like this. Let's say I don't have this in my option. That means I have to multiply this by 1000, and that will give me 250 cm cube. That will give me 250 cm cube. That is the volume of HCl used up. So you can see, very easy, very easy, very, very easy. All you need to do is stick to your understanding of the processes, locate your key. You can see that in this case now, you were given information about iron. If you had used this as your key, everything is going to be wrong from A to Z. This, you were given information about HCl, but it's not usable, but we actually can use our hydrogen here as the key. So that ends question 4. Still on stoichiometry, moving on to question 5. We have a question: when 13.5 gram of a mixture of calcium triazocarbonate 4, that is marble chips or limestone, and quicklime calcium oxide, was thermally decomposed, the mass of residue, that's the remnants, obtained was 9.1 gram. Calculate the volume of CO2 percentage of calcium triazocarbonate 4 in the mixtures. Well, let's get into the question. When 13.5 gram mixture of calcium triazocarbonate 4 and calcium oxide was thermally decomposed. What that means is that I have calcium triazocarbonate 4 and calcium oxide, this as a mixture. This here is a mixture. This here is a mixture, was thermally decomposed. So which means we have to eat this. You eat, you apply it. So normally calcium oxide cannot decompose on eating, but calcium triazocarbonate 4 will decompose. And when calcium triazocarbonate 4 decomposes, it is going to give us calcium oxide. This calcium oxide from the reaction, this particular calcium oxide, not, let me asterisk this, not from the reaction. So what I have is calcium oxide, not part of the reaction. This is part of the reaction, plus carbon dioxide gas. So this mixture altogether was 13.5 gram. Now the residue I have left, that's calcium oxide from the reaction, and the calcium oxide that have been present since the inception of the reaction, is 9.1 gram here. So I was told to calculate volume of CO2 produced. Yes, and to calculate the volume of CO2 produced. Now, looking at this, I said in the last question that anything that does not take part in a balanced chemical reaction, you cannot use that in stoichiometry. So when you look at this is a mixture, and it is only the calcium triazocarbonate 4 here that partake in the reaction. It is only calcium triazocarbonate 4 here that took part in the reaction. This did not take part in the reaction. So telling me that two of them, calcium carbonate and calcium oxide, is 13.5, it means I cannot use this. I cannot use this for this calculation. I cannot use this as my key. When I come here, this took part in the reaction, but I wasn't given a specific mass for the calcium oxide formed from the decomposition. I was given a combined residue mass for the calcium oxide that took part in the reaction and the one that did not take part in the reaction. So I cannot use this as well. But something is very clear here. If you look well, then you ask, what am I going to use as my key? If I started with this 13.5 gram and I ended with this, and it was only carbon dioxide that was formed, I think that should give me the mass of carbon dioxide already, and the mass of carbon dioxide should be what I have at the start, 13.5 minus 9.1, what I have at the end of the reaction. So it means that mass difference is what the difference in mass. This was what I had before. This is what I have as leftover. The difference in mass is what has been converted into carbon dioxide. So this should give me 4.4 gram. So because carbon dioxide is coming from a balanced chemical reaction, calcium triazocarbonate 4, CaO, I'm left with CO2. Because carbon dioxide is coming from a balanced chemical reaction, it means I can then use this as my key, 4.4 grams. So what do I do to my key normal? I convert it to mole. Mole of this is mass over molar mass, and that will give you 4.4. Molar mass of carbon dioxide is 44. 4.4 divided by 44, 0.10 mole. This here is my key. I cannot use this. I cannot use this. So getting to question A, I was told to actually calculate the volume of CO2. Question A, volume of CO2 is the question. Recall that mole equals to volume over molar volume. So in this case, volume equals to mole times molar volume. What is my mole? 0.10 times gas molar volume is 22.4 dm cube. 0.10 times 22.4 will give you 2.24 dm cube. That is the volume of carbon dioxide formed. In this case, I had to get my key all by myself. I had to get that and work with that. All of the values I had in the questions, they are not usable for a key, in that they did not take part in a balanced chemical reaction. So moving on to question B, it says percentage of calcium triazocarbonate 4 in the mixture, and this is also very direct. B, percentage of calcium triazocarbonate. For me to know the percentage, I need to first of all get what is the mass of calcium triazocarbonate 4. When I get the mass, I can now look for the percentage in 13.5 gram. So for me to do this, since this is from a balanced equation, I'll still be using this as my key. And in this case, 1 mole CO2 is stoichiometrically equivalent to 1 mole calcium triazocarbonate 4. So say 1 over 1 equals to 0.10 mole divided by mole of calcium triisocarbonate 4. So in this case, mole of calcium triisocarbonate 4 will be 0.10 mole as well. Now that I have the mole of calcium triisocarbonate 4, I can convert that to mass. Mass is mole times molar mass, and in this case 0.10. What is the molar mass of calcium triisocarbonate 4? That is 100. If you don't know how to calculate molar mass for the Upton time, the link to that lecture video on how to calculate formula mass, how to calculate empirical formula, molecular formula, percentage composition is right in the description to this lecture video. This is 300 plus academy. This is where you need to be to ace your next exams. So 0.10 times 100, this will give you 10.0 gram. So which means that the mass of calcium triisocarbonate 4 in this mixture is actually 10. So the percentage of CaCO3 in the mixture is going to be 10 out of 13.5 times 100, and that is 74.1%. That is 74.1%. That is how it works. No magic in chemistry. It is always pure and direct. Heavenly subject, beautiful subject. So moving on to question 6, we have another question. It says, when 2.10 gram of a mixture of KClO3 and sodium chloride, just like question 5, KClO3 and NaCl, actually no correlation, are thermally decomposed. If we were to decompose thermally, this is what we decompose. This will not decompose. So what we have, KClO3, you are looking at oxygen being liberated. I have 3 here. I need to put 3 here. Then 2 needs to be here. So 2 KCl plus 3O2. Now the sodium chloride is actually not taking part in the reaction. But when potassium triisochlorate 5 decomposes, you have 2 KCl and 3 oxygen moles of oxygen gas. Now the NaCl is just there as part of the residue. So, and we're told that this was 2.10. This was 2.10 gram, but invariably we cannot use it because this is a mixture. We cannot use it in calculating stoichiometrical question. The mass of residue obtained was 1.62. So which means the residue is KCl and the NaCl we started the reaction with. So this was 1.62 gram. That's for the residue. Determine the mass of oxygen liberated. In fact, telling us to determine the mass of oxygen liberated is just like helping us. The mass of oxygen liberated is this. This year combined was 2.10. Now this year combined, the mass had reduced from 2.10 to 1.62. So which means the mass had been converted to oxygen gas. So for question A, mass of oxygen is going to be 2.10 minus 1.62, 0.48 gram. That's what we have. So invariably, this is even looking like our key because it is from a balanced chemical reaction, and now we know the mass. Now B talks about we calculating the mass of sodium chloride impurity in the original mixture, and I can tell you this is where the real question is. So in order to do that, my focus should not be on the sodium chloride because the sodium chloride did not take part in the reaction. Rather, my focus should be on things that took part in the reaction, talking about potassium triisochlorate 5. So in this case, since this is my key, the first thing to do is to convert it to mole. So the mole of oxygen is 0.48 divided by 16 times 2 is 32. It's going to give me 0.015 mole. Now I'm going to use this to unlock my potassium triisochlorate 5, and what that means here is that 3 mole oxygen is stoichiometrically equivalent to 2 mole potassium triisochlorate 5. So if I say 3 over 2, the mole of the oxygen that I have here, 0.015 mole divided by mole of KClO3. So that mole of KClO3 is going to give me 2 times 0.015 mole divided by 3. That is going to give me 0.01 mole. That is the mole of my KClO3. So now that I know the mole of my KClO3, I can get the mass of KClO3. Mass of KClO3 is going to be mole times molar mass, and in this regard 0.01. Potassium triisochlorate 5, if you calculate, is 122.5. So 0.01 times 122.5, you're going to get 1.225 gram. So which means that out of this 2.10 gram, potassium triisochlorate 5 was 1.225. So mass of sodium chloride impurity in the original mixture, okay? So mass of sodium chloride in the original mixture, so they are seeing it as an impurity now. Mass of sodium chloride impurity in the original mixture will be 2.10 minus 1.225 gram, so 0.875 gram. That is the mass of NaCl in the original mixtures, and that just explains that as far as stoichiometry is concerned, and this forms the bedrock of all of the calculations, most of the calculations rather, that you will be having in chemistry. Remember that under this stoichiometry that we've looked at, we've always been using one key here, and that is going to usher us into the next lecture, which is going to be on limiting and excess reactants. In the case of limiting and excess reactants, we will be given 2 keys. This time around, we'll be given 2 information. One of the informations or the key given is the right one to use and not the other one, and that is what limiting and excess reactants is about. Don't forget, subscribe to this channel, because this is where you need to be to prepare vast slick lectures for your various exams. And I can tell you, once you follow instructions, you are going to ace your next exams. Also do well, turn on the notification bell so that at each time that we upload lectures, you can get into the fray of things. Also do well to share with your friends, your boyfriends, your girlfriends, your enemies, your loved ones. They'll be glad you did that for them. From myself and the entire team at 300 Plus Academy, it's bye for now.